Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to predict electron group geometry and molecular geometry. So let's get into this. So in an earlier video I've talked about how to use a particular table. So in order to predict electron group geometry and molecular geometry, usually you have some sort of VSEPR table where you've got the pictures of the molecules and their shapes. And also along with that, you've got the total number of electron groups, you've got the total number of bonding groups or bonds, you've got the total number of electron lone pairs. And so based on the number of total electron groups and the number of lone pairs you have on the central atom, you can figure out from the table whether you've got an electron group geometry or a molecular geometry, or you'll have both, but you'll be able to figure out what they are. Okay, so I'm going to assume you have your table. So if you don't have your table, get your table with the VSEPR theory, molecular shapes, and all of the information on there, and follow along in this video. Okay, so how do I determine what the electron group geometry and the molecular geometry of central atoms are? So we'll start with A. Here I have this molecule. So you'll need to draw the right Lewis dot structure. If you don't know how to draw Lewis dot structures, or you can't really remember, or you need a refresher, please go watch my videos on how to draw Lewis dot structures. And I have videos that go through the steps and plenty of examples. So here's the Lewis dot structure for this molecule here. And so here's the central atom, and we want to determine what the electron group geometry is and what the molecular geometry. Now, the distinction between electron group geometry and molecular geometry is a simple one. Electron group geometry is based on the total electron groups around your central atom. And so it doesn't matter if you have bonding groups or non-bonding groups. So here I have two bonding groups here, and I have a non-bonding group, which is their lone pair. And the thing you also want to remember is that single, double, and triple bonds are all considered one electron group. So this single bond here is one electron group of two electrons in the bond. But here we have a double bond. This double bond is not two electron groups. It is one electron group. This electron group has four electrons being shared between the nitrogen and the oxygen. So the double bond is one electron group. The single bond is another electron group. And I have this lone pair for a third. So I have three electron groups total. So once you know how many electron groups total you have, you look on your table to see what electron group geometry you have if you have a total of three electron groups, because your electron group geometry is based on the total number of electron groups. So if you look at your table for three electron groups, then that will tell you you have a trigonal planar electron group geometry. So the electron group, so EGG, the egg, electron group geometry, that's going to be trigonal planar. Okay. However, the molecular group geometry, the molecular geometry, or what is also known as molecular shape, is only based on the bonded atoms to the central atom. So here we have two electron groups, but we do have this lone pair here. But as far as electron group shape, we ignore the lone pair. So because of VSEPR, we know that the lone pair there is repelling the electrons in the bonds. So those are being pushed away. So the shape is more like this. So you've got your nitrogen, and you've got your oxygen and your fluorine, and like that. I'm not going to draw the rest of it. I just want to draw it to give you an idea of what the shape is like. So because of this, even though so for the molecular geometry, we're only looking at the bonded atoms and what they look like. So in this case, if you look on your table for molecular geometry, you want to look at, okay, so well, how many total electron groups I have? I have 3. But one of them, I have 1 lone pair and 2 bonding pairs. In that situation, your molecular geometry is going to be bent. So I'll put mg for molecular geometry or shape. That's going to be bent. So you can see why the electron group geometry is trigonal planar, because if you include the electrons, the lone pair here, as part of your geometry, then you can see that there is a trigonal planar. It's a triangle, and it's all in the same plane of the board. That's why we call it trigonal planar. But for the molecular group, for the molecular geometry, we don't really care about the lone pairs, so we can cover that up, and we can just look at the shape of the molecule itself, the shape of the atoms, and that is bent. So we see a bent shape for the molecular geometry. So again, the electron group geometry focuses on the, focuses on the total number of electron groups, bonding and non-bonding, or the electron pairs. But your molecular geometry only cares about the bonding groups, or the bonded atoms and what they look like. And that's the shape of the molecule. Okay, so that is how you distinguish or determine and predict what your electron group geometry is versus molecular geometry. So then we can apply that to larger molecules that have multiple central atoms, right? I could actually apply that to these atoms here, but I won't. I will apply it to here. So we have several central atoms. So we have 1, 2, 3, 4, 5, and 6, right? So each central atom in this large molecule has an electron group geometry as well as a molecular geometry, right? So again, we can look at this carbon here. So here we have how many electron groups? 1, 2, and 3. So here we have 3 electron groups. Remember, the double bond is 1 electron group. So this is 1, 2, and 3. So I have a total of 3 electron groups around this carbon. So here, I don't have any lone pairs. So in this situation, if you have no lone pairs, then the molecular geometry and the electron group geometry are identical. That's the only time that you're going to have an identical electron group geometry and molecular geometry, and that's when you have no lone pairs on your central atom. So here, if you look up on your table for electron group geometry, you'll see that under the situation of where you have 3 electron groups, your electron group geometry should be trigonal planar, just like with this one here. The only difference between this one and this one is that this has 3 bonding groups, no lone pairs. This has 2 bonding groups and 1 lone pair. So, but the total number of groups is the same. So if the total number of groups, bonding and non-bonding together, is identical, then you're going to have the same electron group geometry. Okay, but the molecular geometry will be different if you have lone pairs. But here we don't have any lone pairs, so the molecular geometry for this is identical to the electron group geometry. So for this carbon, it's going to, so the electron group geometry is going to be trigonal planar. And the molecular group, the molecular group, or molecular geometry, I keep saying group, is also going to be trigonal planar. All right. What about this carbon here? So again, this carbon is the same as this carbon. We have a double bond and 2 single bonds. So again, we have 3 total electron groups, no lone pairs. So the electron group geometry will be, again, trigonal planar. And since there's no lone pairs on the carbon, the electron group geometry and the molecular geometry are the same. So this will be also the same here. So for this carbon, your e.g. or your electron group geometry is going to be equal to trigonal planar, and your molecular geometry is also going to be trigonal planar. Okay. Next carbon, we have, again, 1 group, 2 groups, 3 groups. We have 3 bonding groups. So again, this is going to be electron group geometry, trigonal planar. And since there's no lone pairs on my central atom, then the electron group geometry is identical to the molecular geometry. So it's going to be trigonal planar as well. So we'll draw an arrow there. So these are identical. And also, let's go up here to this carbon. So this carbon has a single bond and it has a triple bond. So it has 1 electron group, 2 electron groups. Remember, the triple bond and double bonds are considered 1 electron group, not 3 electron groups, 1. So here I have a total of 2 electron groups, no lone pairs. So when you look on your VSEPR table, you'll look up on your table the total number of electron groups being 2, and when you look at the electron group geometry, it will tell you that the electron group geometry is linear. So here, the electron group geometry is linear, a straight line. Okay, since we don't have any lone pairs on our central atom, then the electron group geometry is identical to the molecular geometry. So here we're looking at the shape of the molecule itself, and that is linear again. So the molecular geometry is linear as well. Okay, so we got that done. Then here we've got essential atom, our oxygen. We have 2 bonding groups and we have 2 lone pairs, non-bonding groups. So here we have a total of 4 bonding groups. So when we look on our table and we look up the total number of groups being 4 and we go to the electron group geometry, it should tell us that we have an electron group geometry of tetrahedral. So here I will draw there. So here the electron group geometry is going to be tetrahedral. And now, because we have lone pairs on the central atom, our molecular geometry is not going to be identical to the electron group geometry. So the molecular geometry is going to be different. So we look on our table and we look up the situation where we have a total of 4 electron groups. 2 of them are bonding groups, but 2 of them are lone pairs. So when we look at the molecular geometry on the table, it should tell us that we have a bent shape. So the molecular geometry is going to be bent. And then finally, for this carbon, we have 1, 2, 3, 4 single bonds. Each of them is an electron group. So we have 4 electron groups. So just like the oxygen here with 4 electron groups, this carbon also has 4 electron groups. So its electron group geometry is the same, tetrahedral. So we'll draw this down here. So the electron group geometry is also tetrahedral. Now look here, we don't have any lone pairs on our central atom here. So again, in this case, because we don't have any lone pairs on the carbon, the molecular geometry is going to be identical to the electron group geometry. So the molecular geometry is also tetrahedral. And so that, ladies and gentlemen, is how you identify and predict the electron group geometry and the molecular geometry of your central atom in your molecule. Or if you have multiple central atoms, you can identify what the molecular geometry and electron group geometry of each atom in your molecule. So that's it for this video. I hope you found it helpful. If you did, then please, by all means, like and share the video. Hit that like button. Subscribe to my channel. Make sure you hit the notification bell, and when you do, make sure you click all, and so that way you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. I would love to hear from you. If you have any questions, please ask. If you have any ideas or have a question you want me to answer or a problem you want me to work in a video, then please let me know and I would be happy to do that for you. Thanks for joining me and have a great day.